In this lecture, what I'd like to do is start with Leonard's generalization. So these are the equations we worked out in the previous lecture, where this is the differential power or the total power you get for a moving charge. A charge is moving at a velocity v and acceleration a. And so if we think about it, if we take the non-relativistic case, so if v is much, much less than c, that means gamma is essentially 1. And what you find is that the ratio of V over C is essentially going to go to 0. So what we get then is, for a power, mu 0 q squared a squared over 6 pi c, which is again the Larmor formula. So we've actually now derived this like 3 times. In the previous lecture, we derived it where we said V was 0, that the charge is initially stationary. In this case, we're taking the non-relativistic limit and showing that we get the exact same thing. Okay, so let's look at an example. So example 11.3 out of the book, which is, let's find the differential power and P if V and A are collinear. Okay, so essentially their vectors are pointing in the same direction. So that means that U crossed A is going to be equal to CR minus V crossed into A, which is CR cross A minus V cross A. Now, if they're collinear, that's 0. So we get CR crossed into A. Okay, so that simplifies it a little bit. So now let's take a look at the differential power. So that quantity squared over R dot CR minus V, that quantity to the 5th power. Okay, so let's take a look at some of these terms. So what we have is R cross A is going to be R dot A in the R direction minus A. And then if you were to square it, then what would you get? You would get R dot A, R dot R minus 2 R dot A times R dot A plus A squared. So we saw this in a previous lecture, that this n turns out to be A squared minus R dot A quantity squared. Okay, so let's update the formula. We have q squared c squared over 16 pi squared epsilon naught a squared minus R dot A quantity squared over C minus R dot V to the 5th power. So we did actually, no, that's right. So we didn't do anything. We just multiplied that out. Okay. So let's say that V and A are in the z direction. So what does that mean? Well, if this is x, y, z, so then v is in this direction, r is just pointing off in some direction at some angle theta between them. So that means that r dot A is equal to A cosine theta, and r dot V is equal to V cosine theta. Just worked out the dot products. Okay, so let's put those into the equation now, and what we have is dp d omega, which is q squared c squared a squared sine squared theta. Well, actually, sorry. We can back up a little bit. Minus a squared cosine squared theta over 16 pi squared epsilon naught c to the 5th power 1 minus v over c cosine theta to the 5th power. So I just took a factor of the speed of light out of the 5th parentheses. So anyway, so a squared minus a squared times cosine squared is a squared sine squared. So we get q squared, c squared, a squared, sine squared over 16 pi squared epsilon naught c to the 5th power 1 minus v over c cosine theta to the 5th power. Okay. So let's make some substitutions. Epsilon naught c squared is 1 over mu. I'm going to call v over c beta. If v is equal to 0, beta is equal to 0. If beta is approximately 1, that means that where the charge is moving close to the speed of light. And what we should get then is this cone of radiation being emitted by the charge as it moves along the z-axis. Okay, so now what I want to do is to integrate. So this is essentially the formula we have. We could clean it up a little bit by canceling some of the. Why don't we do that? Canceling some of the speeds of light. So what we get is the differential power is mu 0 q squared a squared sine squared theta over 16 pi c 1 minus beta cosine theta to the 5th power. So that's the functional form for that cone of radiation that I just mentioned. Okay. So now let's look at the total power, P, which is now the integral of my differential power over the solid angle. And in that case, if we put everything in, I get mu 0 q squared a squared sine squared theta over 16 pi c 1 minus beta cosine to the 5th power. And then I have a factor of sine theta, d theta, d phi. Well, the d phi part's going to be easy because there's no phi dependence. So you can integrate that out and get a 2 pi. And what we're left with is mu 0 q squared a squared over 16 pi squared. There's a squared in there. C 2 pi integrating from 0 to pi sine cubed over 1 minus beta cosine theta to the 5th power d theta. Okay, so that's that's the integral we have to solve. So let's make a substitution. Let's say x is equal to cosine theta, dx is equal to minus sine of theta d theta, which leaves me with mu 0 q squared a squared over 8 pi c, integrating from positive 1 to minus 1, minus 1 minus x squared over 1 minus beta x to the 5th power dx. Okay. So let's keep attacking that integral. So if we, okay, so we can rearrange the limits. And get rid of that minus sign. Okay, so now what you have to do is basically do an integration by parts. And when you do that, you get a power, which is mu 0 q squared a squared gamma to the 6th power 6 pi over c. Remember, gamma is 1 over the square root of 1 minus beta squared. Okay. So in the end, this is the result that you would get for the one particular case where the velocity and the acceleration are in the same direction, which is a good, case to work out. Now this would not be applied to something like centripetal motion, but if you have a charge that is moving in a line, more times than not, that acceleration vector is going to be pointing in the same direction as the velocity vector. And if that is the case, then this is the result you would get for collinear velocity and acceleration.